disappointments. You will be measuring something and your sigma levels will be great, and customer will be measuring something else, and the business will be down, right? If you really want your metrics to represent what is actually happening in the field, then you have to measure the characteristics which are important from your customer's point of view, right? And then once you understand the characteristics, it is dimension, sometimes it is the timeline, sometimes it is the number of errors in your report. It could be any kind of non-conformance, basically, right? We call it the defect. So that particular characteristics, what kind of data it is, you must know. Data type. That's why we learned the data type under the measurement plan. Data can be continuous, data can be discrete. Anything that is measurable is continuous, anything that is countable is discrete, right? And also we learned 4 types of measurement scale. The measurement scale, when you go up the order from nominal to ordinal, ordinal to interval, interval to ratio, then your data will support you to a great extent, right? You can always make a choice out of the 4, nominal, ordinal, interval, ratio. And the advantage of going with the ratio is you can do all sort of mathematical operation, and it will make sense in real life, right? And then another thing you learned is operational definition. What is operational definition? A clear and concise statement about the characteristics to be measured. I want a work to be carried out by one of my team member. Now I pass on the instruction. And what is the point in simply complicating the statement and confusing the person who is going to produce result for me? Instead of that, make a simple, clear, concise statement so that nobody reading your statement will have the chance to undergo any kind of confusion, right? No chance at all, so that they can easily understand and then do the work the way it is required. That is called operational definition. Why are we so much concerned about all these things? Because we want our data to be worthy, right? And then you went on and learned about the sampling techniques. And there are 2 types of sampling technique. One is probabilistic, another one is non-probabilistic, right? So within probabilistic, you have learned the random sampling, systematic sampling, and then stratified sampling, and then cluster sampling. And we also understood that we cannot say this is the best sampling technique. It is always you as a process owner, you as a problem solver, after thoroughly understanding the problem, you need to make a choice on the sampling technique. You can also create your own sampling technique based on your knowledge about the population, knowledge about the problem, and the strength and weakness of the various sampling techniques. And on the other hand, non-probabilistic sampling techniques such as convenience sampling, purposive sampling, snowball sampling, and voluntary sampling, and all those you learned. And then we also discussed about sample size. And generally, companies have the thumb rule of sample size equal to 30 and above. 30 and above, always safer, right? But if you really wanted to be very optimistic, right, in terms of the sample size, then you need to understand the dynamics of the sample size, right? So sample size plays around your confidence level, power of the test, and the kind of difference in the statistics you wanted to validate. So it's very important you understand how the sample size varies with respect to the other terms. And mainly the sample size is a function of the nature of the population. Sample size is a function of the nature of the population. For example, suppose I want to understand about the students in this class, the nature of the population, and is known to me. I know each and every one of you, by name and by everything. So the population is known. Now I can work out an appropriate sample size. Similarly, when it comes to a big population, right, a particular characteristics, then the nature of the population needs to be understood. How do you know the nature of the population? By visualizing the data, right? Once you visualize the data, if you understand your population, is symmetric, then your job is less. If the population is symmetric means what? Whatever you see on the right side of the, you draw a center line, and whatever you see on the right side, the same thing you will see on the left side. Normal distribution is a symmetrical distribution. Uniform distribution is a symmetrical distribution. Under such cases, even a lower sample size can help you to understand the reality. Right? Sample size of 5 will be sufficient. You don't have to go for 30 and all. What if the population is unsymmetric, right? For example, it's a variable distribution. It's an exponential distribution. Under such situation, you may have to go up to a sample size of 50. And RK has developed a beautiful template which can guide you, because visualizing the data and all those things, if those are not possible with whatever information that is available in your hand, if you know how to make use of these templates, then you get an idea on the the sample size. And also you must learn one more theorem called the central limit theorem that today I will be teaching all of you. Then with the knowledge of the central limit theorem and knowledge of the different types of distribution, again, that will be taught by RK. And by making use of the template, I'm sure as a black belt, you will be able to do very well in terms of deciding on the sample size. So fundamentally, sample size depends on your confidence level and the confidence interval. So what is confidence level? What is confidence interval? We are going to discuss today, right? And for a fixed confidence level, let's say I want a 95% confidence level. At the same time, I don't want to go for a higher sample size. Then I take a very minimum number of sample. Then the consequence will be your confidence interval will be wider. Isn't it? So if you want a higher confidence level, at the same time, you want your confidence interval to be narrower, then you must preferably take a large sample, right? And this is the dynamics between your sample size and the confidence level and interval. So for a given confidence level, given power and the difference in the statistics to be validated, you can judge on the sample size. So this is about the step number 4 you learned in the measurement plan or data collection plan. And then assign the job to a particular person, develop a check sheet having all these guidelines, and then he can collect the data for you. Then we moved on to step number 5. What is step number 5? Validating measurement system, right? MSA, measurement system analysis. And there, first of all, we need to know what is measurement system. Measurement system, all the elements put together is called the system. Now also the training program, we are functioning as a system. It is not that you alone responsible for the result. It is not the trainer alone is responsible for the result. All of us are responsible. The course materials that are shared, the templates that are shared. If one out of the element, all the elements is going wrong, then end result will be wrong. Similarly, measurement system analysis has several elements that includes the equipment, the appraiser, the part that is getting measured or the characteristic that is getting measured, and the operational definition you are using, and the environment under which you actually collect the data. If anything goes wrong, then your data will have a huge error, right? A measurement system is considered capable if it is accurate and precise in its readings, right? Accuracy means closeness to the true value. Precision means consistency in the readings, right? Irrespective of the environment and irrespective of the change in the operator and many things, your readings have to be consistent, right? And the closeness to the true value, we call it accuracy. And the consistency in the reading, we call it precision. If your readings are not accurate, it means the difference between the true value and the observed value is high, isn't it? And this difference is called bias. The expectation is bias should be minimum, bias should be 0. Your readings will be considered unstable if the bias is not constant over a period of time. Your readings are considered to be non-linear if the bias is constant over the range of the measurement, right? Make sure your readings are stable, make sure your readings are linear, and make sure the bias is minimum, and to the extent possible, make it 0. But once you understand the dynamics of the bias, if the bias is a constant one, then working out a calibration procedure and then setting the calibration frequency, all that will become easier for you, right? And do the calibration, take care of your equipment, take care of the maintenance procedures. Your equipment, your measurement system will start giving the error-free reading. That is the bias-free readings. So you can be more and more accurate, right? And then as far as the other part of the measurement system, we are talking about accuracy. The other part of the measurement system is precision. What is precision? The consistency in the reading. And there comes repeatability and reproducibility. The repeatability and reproducibility put together is called precision. If the repeatable, see, there is a difference. Yesterday there was a confusion between repeatability and repeatability error. I want repeatability. If I don't achieve the repeatability, then the degree to which I am inconsistent is called repeatability error. Similarly, reproducibility error. Both these errors put together is called precision error. This precision error must be compared against the range of tolerance within which you are trying to produce or within which you are trying to operate. So you have precision compared against tolerance. And now the ratio obtained is called precision tolerance ratio. And this is what we call it as gauge R&R, gauge repeatability and gauge reproducibility. This gauge R&R value should be less than 10%, right? It is applicable to all industries. If the gauge R&R value is less than 10% and the NDC is more than 5, your measurement system is considered capable as well as adequate. If the gauge R&R is more than 30% and your measurement system is definitely considered not capable, and then you must think of improvising your measurement system. In fact, you should not use the data that you have collected using such a measurement system. And then 10 to 30%, it's conditionally acceptable. Conditionally acceptable, you can make use of generic reasons like budget is high and all those things. But the technical reason is you should know the position of your control limit with respect to the specification limit. If the control limits are seen far inside the specification limit, then 10 to 30% can also be allowed, can also be considered okay. Why? Because even you have the 10 to 30% of the uncertainty zone, still you are confident that you can restrict the type 1 error and type 2 error by keeping your control limit well inside the specification limits, right? And then NDC is another thing we discussed, right? What is NDC? Number of distinct data categories. This will tell you whether your measurement system is adequate to be used in the entire range of the measurements or not. And NDC has to be 5. And NDC depends on the resolution of the equipment, the least count of the equipment. If you have a better least count, better resolution, then obviously your NDC will improve. And then we proceeded to learn the baseline performance. One metric of baseline performance was taught to you, right? And you did an experiment, GEMS experiment, through which you understood how to calculate DPMO, defects per million opportunities. You can use this metric, DPMO, to actually know when your data is discrete data, countable data. Defects only you count, isn't it? When your data is continuous, the DPMO still can be calculated, but then it cannot be a direct measure. Then you must go for CP/CPK, PP/PPK, and yield metrics, right? So it is basically the data type that guides you on the choice of the tool. If your data is discrete data, countable data, then DPMO is a best metric. And that is what you did, all of you, yesterday. You counted the color defect, you counted the crack defect, you counted the count defect, you also counted the shape defect and the taste. All of them are countable data. So you calculated DPMO and finally interpreted the DPMO to sigma level. That means everything is finally same. Whether it is DPMO or it is CP/CPK or it is PP/PPK or it is yield metric, all of them are going to be same. So today you will be learning the yield metrics. You will also be learning the CP/CPK and PP/PPK, right? And I think this is what we learned yesterday in essence, right? I hope you had understood fully on all the tools which we learned yesterday. And if there are any questions, I'll be happy to answer. Otherwise, we can move on to our today's job.